On to Lewis structures. All right, so hopefully a good portion of this will be a refresher and a review from what you did in prep chem. We are going to expand on this though. So this is why it's hopefully the actual drawing of Lewis structures will be a refresher, because we're also going to now expand our octet, and we are going to look at something called formal charges, and we'll be able to use formal charges to assess what makes a better structure. All right. So we know that each element has its own particular number of valence electrons, and we can draw all these little dots, and we can match up the dots. So like, I can have a chlorine with all its little dots, and I've got this other chlorine with all the little dots. All right, and then, I can do this. All right, and that shows that I've paired up those two dots. And then I can draw my Lewis structure like this, okay? Now, in a preparatory class or a high school class, you may have been taught that you can draw those two little dots paired up with each other like I just did. That's prep chem, okay? I expect you at this stage of the game to understand that every line you draw represents a bond, and every bond represents two electrons that are being shared. All right, I don't want to see any paired up dots. The only dots that should be on your structures are lone pairs. All bonds need to be the dashed lines, okay? Dots are lone pairs, lines are bonds. So we have a few different things going on here. We have our bonding pairs. So these are the pairs that are involved in bonds, okay? So that chlorine example, yeah, I've got, actually, let me color code this. All right, so with my chlorine here, I'll draw my bond in red, okay? All right, and then I've got my lone pairs. These are electron pairs that do not participate in bonding. So here, okay, there's my lone pairs. They are not participating in bonding. And then there is my bond order, which is the number of bonds. So here, my bond order is 1, because I have that single bond there. Okay? Now you should be familiar with how to draw a Lewis structure. So these are, the general rules. If you are needing a refresher, you can look through them. But one thing that's key is you have to make sure that you use up all of your valence electrons. No more, no less. So it's good to total your number of valence electrons before drawing a structure. All right, you're going to put stuff around each other. Things with the lowest electronegativity go in the center. Higher electronegativity become surrounding atoms. Surrounding atoms are very good at pulling electrons toward themselves, and so higher electronegativity, more electron greed, more ability to attract electrons to themselves, so they yank that density. One exception here is hydrogen. Hydrogen sometimes has a lower electronegativity. It can never go in the center because hydrogen can only ever have one bond. Make sure that you connect everything with at least one bond, because if we're not bonded together, we don't have a structure, and each bond is 2 electrons. And then you just distribute the rest of the electrons to make sure that you are obeying the rules and making sure everything, uses up your valence electrons. Now to start off with, you want to make sure you have an octet. But as we're going to see in a little bit here, when we get to period 3 and beyond, we can actually start violating that octet. Or there's a few cases where there's something that maybe doesn't want an octet. And so we'll look at some of those cases in a minute here, where we may not necessarily obey the octet, which are things that you should have learned in prep chem. Things like boron, which is famously electron deficient. Or if I only have 2 things bonded together, I might not necessarily, I may be obeying the octet, but I may not necessarily be obeying like the way they like to do things, okay? So before we expand the octet, the main one that you should remember from prep chem is boron. Boron is famously electron deficient. It is perfectly happy with only 6 electrons around it, okay? Some helpful hints: hydrogen, always going to only form one bond, okay? This is a hard and fast rule. Hydrogen only has a 1s orbital. It can only hold 2 electrons. You cannot get lone pairs around hydrogen, nor can you ever get more than a single bond. If you ever put lone pairs on hydrogen, or you ever put multiple bonds to hydrogen, I will cry, because you can't do it. And that's something you should know from before. Carbon likes to form 4 bonds. It's pretty inflexible. There are a few cases like where it's just carbon bonded to one other thing instead of being, a whole bunch of extra atoms, where it might not have its 4 bonds, but carbon is pretty rigid. Nitrogen likes 3, oxygen likes 2. These guys are more flexible though. We can get, deviations from that. There's things like the hydroxide ion, where it's just OH, or the hydronium ion, H3O+, the ammonium ion, NH4+. So oxygen and nitrogen, they prefer to have 3 bonds and 2 bonds respectively. However, that's not a hard and fast rule. They're a little bit more flexible. As surrounding atoms, halogens will form 1 bond. Fluorine is the most electronegative element, so it's always a surrounding atom. Okay, so those are some helpful hints as you try to put things together. All right, so let's take a look at some structures here. All right, let's do an easy one to start with, nitrogen trifluoride. So if we sum up our valence electrons, 5 from nitrogen, 7 each from 3 fluorines, gives us a total of 26 electrons. Now, if you are not very comfortable with this yet, one thing you can do with your electrons is you can keep a ledger. So I'll put my atoms relative to each other, and then I'll connect everything with 1 bond. Each bond is 2 electrons, so 3 bonds times 2 electrons. Now I've used up 6 electrons. I have 20 electrons left. Okay. Fluorine, it's a halogen, it's a surrounding atom. It likes that 1 bond, so I'm going to leave that alone. Now I know each fluorine needs to have its octet. So 1, 2, 3, 4, 5, 6 more electrons around each fluorine. Okay. So I have 6 electrons around each of 3 fluorines. 6 times 3 is 18. I have 2 electrons left. Just so happens that my nitrogen needs 2 electrons to fill its octet. Okay, so you can keep a ledger. All right, so here's one to try. Okay, so you end up with 4 plus 4 times 7, 32 electrons. All right, see if you can draw this one. Okay, you should get something that looks like this. I like symmetry, so I put the chlorines and fluorines opposite each other. You can put them next to each other. It doesn't matter. So carbon's got its 4 bonds. Chlorine and fluorine, halogens, they are surrounding atoms here. Voila. Okay. Here's another one. Okay, so now this one, you have to think about it. So when you sum up the electrons, you're going to get 14 valence electrons that you have to keep track of. Now, we've got the CH4O. So what I've seen students do is they try to do this, because the CH4, and they do this. What is wrong with that structure? Why is that bad? Well, if you said it's because hydrogen has 2 bonds to it, you are absolutely correct. So what we're going to do is we're going to swap these. And we're going to do that. Okay? So sometimes when you have a formula, it doesn't always give you information about how the structure is supposed to look. And so sometimes you have to play with it to make sure that you're not violating any rules and that everything is going to fall out okay. And then we'll put our lone pairs on our oxygen there. Okay. All right, now here's one to try. There's 2 different structures you can draw for this one. Okay, so see if you can figure out the 2 different structures that you can draw for this one. All right, so let's see. Okay, so you can do this. So this is what I see a lot. And then we've got 6 hydrogens. 1, 2, 3, 4, 5, 6. We need 20 electrons. So we've used 2, 4, 6, 8, 10, 12. Wait, 2, 4, 6, 8, 10, 12, 14, 16. There we go. I can count. And then our lone pairs on oxygen give us 18, 20. Okay, the other structure you can draw is this one. Okay. This structure is methanol. This is ethanol. This is dimethyl ether. Okay. So those ones with the OH on the ends, those are alcohols, and the one with the oxygen in the middle, that's an ether. Okay. Now, here's a couple others. Carbon monoxide and nitrogen monoxide. So what's happening here? Well, we have 10 electrons. We need to make sure that we get our octet. So when I do carbon monoxide, I'm going to get something that looks like this. So I mentioned that carbon's pretty rigid. It doesn't like to deviate from its 4 bonds. Well, in this case, there's nothing more that I can do because there is no such thing as a quadruple bond. And if I did have a quadruple bond, then I wouldn't be using all 10 electrons either. All right. So in situations like this, yeah, we can violate the preferences that carbon has, but in pretty much everything else, carbon does not want to deviate from its 4 bonds. It doesn't like lone pairs. It doesn't. When we do chemistry with it, that's what we see. Carbon and lone pairs, they're not friends. Okay. And then my nitrogen monoxide, this one's interesting. So I have 5 electrons from nitrogen plus 6 from oxygen, giving me 11 electrons. I'm going to have an odd number of electrons. Okay, so this is where I get something called a radical. So my 2 structures for this, I can draw the radical on nitrogen, or I can draw the radical on oxygen. And so I don't have a full octet on nitrogen in the first structure, and I don't have a full octet on oxygen in the second structure. And that does happen occasionally, that we get these crazy compounds where there's nothing I can do. There aren't enough electrons. We can't get an octet there. These are highly reactive. So when we talk about like these NOx compounds that are up in the atmosphere, where that X there is a certain number of oxygens, we end up with these radicals because we end up with an odd number of electrons. And so these are super reactive, which is part of why they're so terrible up in our atmospheres, because they will react with things because they're just unstable radicals. So do they form? Yes. Do they like to form? Well, not really. So as soon as, they can react with something else, they do. All right, so here's a few others for you to try. So I want you to pause, and I want you to draw the structure. Okay. So we're going to get... Okay, there's our water. Here I gave you some structural information. I gave you that carboxylic acid, all right? So you're going to have the carbon with the 3 hydrogens. So that was nice, and I wrote it to give you that. All right, so that's COOH, this functional group right here. That's that carboxylic acid, and that is that part right there. So when you see COOH, you're going to have that carbon double bonded to an oxygen and then bonded to an oxygen and a hydrogen. Okay. Boron trifluoride. Again, this is where we get that famously electron deficient. This is your structure. Okay, so boron does this. Boron prefers just to have those 3 bonds like this. Now, technically speaking, could I lose a lone pair off fluorine and double bond the boron, thus giving everything a full octet? Absolutely, you can do that. However, that's not the best structure. Boron is perfectly happy like this, and remember, fluorine is always a surrounding atom, and when fluorine's a surrounding atom, it gets one bond. Fluorine doesn't like double bonds. So we get this structure. When we talk about formal charges in a little bit, there's actually a way we can calculate the formal charges and justify that this is the better structure as well. Okay, and then our last one. Okay, every single one of these is a Lewis structure that stems from prep chem. Okay, nothing I gave you in these examples is anything harder than I would have given to a prep chem class. So if you struggled with these, you've definitely got some catching up that you need to do and a lot of practice that you need to do on your Lewis structures, because this should all be old hat by now, okay? Because now we're going to bump it up a notch. Now we're going to talk about formal charges. So a formal charge is the charge an atom would have if the bonding electrons were shared equally, okay? So we calculate this by taking the number of valence electrons minus 1/2 of the bonding electrons plus the total number of electrons as lone pairs. So when I look at that boron, trifluoride, okay, I can calculate the formal charge on boron. So what I'm going to do is I'm going to take, so boron has, if I look on the periodic table, oh, boron's in group 3A, so boron has 3 valence electrons. So I'm going to take my number of valence electrons minus 1/2 of the bonding electrons. So we have 1, 2, 3 bonds, so that's 6 electrons, so 1/2 of 6. I have no lone pairs, plus 0, so 3 minus 3 is a formal charge of 0. Okay, and then I can put the formal charge on the boron. Okay, my fluorine, we have 7 valence electrons minus 1/2 of 2 because it only has one bond, 6 lone pairs. 7 minus 7 is 0. That is an excellent structure. 0 formal charges everywhere. Now, I mentioned that we can, there's another valid structure. This is a valid structure. It's not a good structure, but it's valid. Okay, so I have 2 types of fluorines here. So I'm going to label, this is fluorine 1, and this is fluorine 2. Because I've got fluorines with a double bond and fluorines with a single bond. Okay, so first we're going to take a look at that boron. Okay, so I still have 3 valence electrons. Now I'm going to take 1/2 of 8. And no lone pair still, so plus 0. Because I have 4 bonds, so I have 8 electrons in my bonds. Okay, so that's going to be 3 minus 4, which is going to give me a formal charge of minus 1. Okay, so boron's going to get a formal charge of minus 1. All right, so now my fluorine with the double bond. We still have 7 valence electrons. Now we're going to do 1/2 of 4 plus 4. Okay, so 1/2 of 4 is 2, plus 4 is 6. So 7 minus 6 gives us plus 1. Oh, okay, so now I have a plus 1 here. And then we already did the formal charge for the fluorine with a single bond and 3 lone pairs, and so that was a 0 and a 0. Okay, so my formal charges sum to neutral because 0 plus 0 plus minus 1 plus plus 1 gives me 0, which is good because this is a neutral compound. But now instead of having 0 formal charges on everything, I've got formal charges on my boron and on my fluorine. And not only that, which element is more electronegative, boron or fluorine? Well, fluorine is. And we gave a +1 formal charge to fluorine. Not a happy situation there at all. Okay, the more electronegative element is going to want to have the negative formal charge. So that is why that is a bad structure. All right, so when I look at these formal charges, our bonding electrons are assigned equally, all right, as if we were nonpolar covalent, which is why each atom has half of them, okay? We're assuming equal sharing there. Okay, so now let's take a look at sulfur trioxide. Okay, we can have resonance here. I'm just going to draw one of them. Okay. All right, so here I have oxygen 1 is the one with the double bond, and then oxygen 2 have the single bond. Okay, so let's do some formal charges. So let's look at sulfur. Sulfur has 6 valence electrons minus 1/2 of 8 plus 0 lone pairs gives me a +2. Ooh, that's a high formal charge. Okay. All right, let's look at oxygen 1. Also has 6 valence electrons. 1/2 of 4 plus 4 gives me 0. That's why oxygen prefers 2 bonds and 2 lone pairs, is it gets a formal charge of 0. Okay, so I have a formal charge of 0 there. Okay, and then my second type of oxygen, 6 valence electrons minus 1/2 of 2, because I just have a single bond there, so 2 electrons. And then plus 6. Okay, so 6 minus 7 gives me -1. So each of these have a -1. All right, now sulfur trioxide is a neutral compound. -1, -1 plus 2, and a 0 gives me 0. This is not a very happy structure, though. That's a lot of formal charge. What if I did this, though? But wait, Professor Stanfield, sulfur has 12 electrons around it. We can't do that. Yes, we can. Sulfur, if you look on the periodic table, is in period 3. Okay, so what do we know about energy levels? What do we know about orbitals? In period 3, we have an n equals 3, which means we can have L values of 0, 1, and 2. An L value of 0 is my s orbital, an L value of 1 are my 3p orbitals, and an L value of 2 corresponds to d orbitals. This means that in period 3, even though we have not filled the d orbitals, we don't fill those till period 4, they exist. So my period 3 elements, they don't use the d orbitals for their ground state electron configurations. However, those d orbitals, they exist, they're empty, we can access them. And so period 3 elements and beyond, all right, we can expand the octet. Okay, a lot of times the expanded octet involves simply pairing up every one of those dots. So sulfur, I would have 6 dots around it because it has 6 valence electrons. So I'm going to pair every one of those up. 6 times 2 paired up is 12. Ergo, I have 12 electrons around my sulfur. So yes, we can indeed get 12 electrons. Now let's check this based on our formal charges. Okay, so my sulfur, I'm going to get 6 minus 1/2 of 12 plus 0 is going to give me 0. That's a happy formal charge. All 3 of my oxygens are equivalent. 6 minus 1/2 of 4 plus 4 is going to also give me 0. 0, 0, 0, 0. Which one's the better structure? The expanded octet is. Okay. All right. Let's see here. So I've got this OCN, the cyanate anion. There's 3 structures that we can draw. Let's figure out which one's the best. Okay, so I can draw this one. Okay. I can draw this one. And I can draw this one. Okay, so what I want you to do is, now that you've watched me calculate formal charges a couple of times, I want you to calculate the formal charges. Okay, so pause, take a moment, and calculate the formal charges on each element in each one of these structures. Okay? All right, let's see how you did. So you should get a -1 here, a 0 here, and a 0 there. Okay, and this looks good because OCN has a -1 charge, and 0 plus 0 plus -1 is -1. Okay, so that one looks good. All right, over here you should get a 0, a 0, and a -1. Perfect. And then over here you should get a +1, a 0, and a -2. Okay, so now, before we figure out which one's the best structure, can you figure out which one is the worst structure? Yeah, so we're going to have structure 1, structure 2, and structure 3. Okay, so which one's the worst? Structure 3 is the worst. Why? Has the highest formal charges. And also, what's more electronegative, nitrogen or oxygen? Oxygen is. And so this would not be a happy situation for oxygen to carry a +1 and nitrogen to carry a -2. Okay? All right, so which one's the best? Well, when we look at structures 1 and 2, they both have 2 zeros and a -1. So this is where it comes down to the electronegativity. So which one's the best? Well, structure 1 is. Okay? Oxygen is more electronegative than so it is happier with -1. The -1 formal charge. Okay, so that's how we figure out which one's the best structure. All right, and so now those expanded octets. All right, so these are, again, elements beyond neon have these available d orbitals. They're empty, they're there, we can access them. So again, we're looking at IE, period 3, and beyond. Okay, so we can access empty space. Okay, so here are 3 examples. I want you to try these. Okay, keeping in mind, I made them, relatively straightforward. Fluorine, remember, most electronegative element, it does not want to have anything more than that single bond to it. Okay, so don't violate the single bond for fluorine. And then I mentioned that halogens in general, if they are surrounding atoms, they're going to get a single bond. It's the same thing with that chlorine there in the phosphorus pentachloride. Just give each of those chlorines a single bond. All right, see what you can do. Okay, so your xenon difluoride should have 22 electrons, and it's going to look like this. Okay, so there's that single bond for each of the fluorines. So we have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So we still have 6 more electrons that we need to deal with. Well, xenon can expand its octet, so I'm going to do 1, 2, 3, 4, 5, 6. There's your structure. Okay. This one, 36 electrons. It's the same thing. Go ahead and take each of those fluorines, give them their single bond. And then you end up with 2 left over, or 2 sets of lone pairs left over, so 4 electrons left over, and you get that. Okay? Expand that octet. And then our last one here. Again, give those halogens their due, a surrounding. Voila, there's your expanded octet. Okay? All right, now here's a challenge for you. There's 2 ways you can draw sulfuric acid. There's a version with an expanded octet, and there's a version without an expanded octet. Draw both, and then calculate formal charges and see which one's better. So pause, and I'll show you after you unpause. Make sure you pause and try this. As I keep saying, if you don't try problems on your own, you're never going to learn. If all you ever do is copy what I write, it's never going to sink in. So pause, draw both of them. Okay, hopefully you all listened to me and you paused and you tried it on your own. So here is the version that does not expand the octet. Okay, you'll get your formal charges. You'll get a 0 here, a 0 here, a 0 here, a 0 here, a -1, a -1, and a +2. Okay? All right, and then the one where we do expand the octet, it'll look like this. And sulfur is the only element here that can expand the octet. Okay, and here's your formal charges. Hydrogen's always going to be a 0, so I'm not going to bother writing that one. I put that on the wrong side. Boom. Which one's the better structure? The bottom one. And in fact, when we actually start to mess with sulfuric acid and the hydrogens come off, all right, they're going to come off, obviously, the 2 oxygens. And those 2 oxygens are now going to each be carrying a negative charge. And it's much more stable with the 2 double bonded oxygens once we start reacting sulfuric acid. So formal charges. There's your justification for why that expanded octet is better. All right, so now our ions. Okay, so when we do ions, we have to account for missing or extra electrons. So anions, we add electrons equal to the charge on the anion. Cations, we subtract equal to the charge on the cation. So again, this should hopefully be something that you have heard before. This should not be a surprise. We do ions in our prep chem classes, but let's practice a couple. So here's the carbonate anion and the hydronium anion. So carbonate, you can do 3 resonance structures for it. Just draw one because the charge and the formal charges are the same no matter which resonance structure you have. So pause, try these. Okay, so here's one resonance structure for the carbonate anion. Now, what you may have learned is to do these brackets and the charge outside the brackets. Well, now that we know formal charges, we can actually do this a different way. So if you calculate the formal charges on these, and you write the formal charges, you don't actually have to put those brackets. Because I'll do a 0, a -1, and a -1. There's my overall -2. Okay, and then my hydronium ion. Okay, I'm not going to bother putting the formal charges on the hydrogens because again, hydrogen will always have a formal charge of 0 because it can't do anything beyond the single bond. And so I'm just going to put the +1 formal charge there on the oxygen. Okay. All right, now resonance. So you may have learned this. So I mentioned that there's 3 resonance structures that we could have drawn for that carbonate anion. So when you have 2 or more Lewis structures and that cyanate, the OCN, that had 3 resonance structures, okay? You can't adequately depict them by a single one. Now, the cyanate, the resonance on that is a little bit fussier because in that case, we did have different formal charges. And so one resonance structure was actually better than the others, okay? True resonance, though, everything's equivalent. And so it doesn't really matter, okay? And so we differ only in the position and bonding of, those bonding and lone electron pairs. So technically what we drew for thiocyanate, or for, not thiocyanate, but for cyanate was a resonance set, but it wasn't all equivalent, okay? And so all the structures did not have the exact same energy there, okay? A resonance hybrid, we get this weighted average of the resonance structures, and the electrons are delocalized, okay? All right, so let's take a look at a couple. So again, carbonate. Okay. All right, and then we get the -1, -1, 0, 0. All right, and we draw these double-headed arrows to show, hey, look, we're doing equivalent structures here. -1, -1, 0, 0. And I have one more spot that I can show that double bond character, and that is here. -1, -1, 0, 0. Okay. All right, another one is benzene. So I'm going to draw carbon framework structure. So I can draw my double bonds there. Okay, so every end and bend is a carbon with the maximum number of bonds, so the maximum number of hydrogens attached to it. So if I've got carbon, if I have a carbon here with 1, 2, 3 bonds, then I would have one of the hydrogens there. So 6 points, 6 hydrogens, or 6 carbons, each with 1 hydrogen. Now, I can draw the resonance hybrid here. So the way this is drawn usually is just with a circle in the middle, showing that those double bonds in that ring are all completely delocalized and they're equally spread throughout. Okay? All right, and so that is our Lewis structures, our formal charges, and our resonance there. So hopefully only the formal charges and the expanded octets were new. Hopefully the Lewis structures themselves, the concept of resonance, the ions, hopefully those were a review So then you can focus on the new stuff, which is the formal charges and expanding the octet.